So today our topic is polynomial functions of higher degrees. And we're going to start by taking a look at just some basic graphs. And what I want to do is consider their end behaviors. Our idea here is we're going to be looking for different patterns, looking to see if I could just look at, let's say, the function and determine what the end behavior would look like. So if I look at our top two graphs look really pretty much the same. I'm just noticing that the equations are a little bit different. We have 2x cubed and x to the fifth. If we were looking at perhaps the end behavior for both of them, I could say as x goes to negative infinity, I see my functions going to negative infinity. So the limit doesn't exist, but my graph is pointing down. And if I were to look at, and again, this is both of the top two functions, the right-hand side, and say, what's the end behavior in the positive direction? Well, the end behavior points up. It goes to positive infinity. Again, the limit will not exist. It is not approaching a solid number, but I can see that the direction is going up, and that goes for both of them. If I look at the next two graphs, the difference in the next two graphs, I can see one big major difference is now they are both negative. So I have negative x cubed for the one on the left and negative 1/2 x to the 7th. So I'm noticing now it almost looks like end behaviors are switching. So if we did the same thing from above, taking a look at when the function goes to negative infinity, well, this time I see it's going in the positive direction. And if I were to look at the end behavior as we were to go to the positive side, well, now this time it looks like it's going to negative infinity. And again, none of these limits actually exist. There is no number it is approaching. It's just telling us which direction it's going in. Trying to make some more comparisons, if we take a look at the last four functions, now, something I'm noticing, if we just take a look at the left graphs compared to the right graph. So the left ones, again, are positive. The right ones are negative. So I can notice a difference there. Some are opening up or some are opening down. And all four of these, this time I can see have even exponents versus the one above had odd exponents. So again, if we're doing the end behavior, and I'm looking at the ones on the left just because they look like they're going in the same direction. So as x goes towards negative infinity, again, limit doesn't exist, but I could tell you it's going in the positive direction. Whereas if I were to look at the functions and I go to positive infinity, well, same thing. Limit doesn't exist, but it's going in the positive direction. Now, different from the ones on the right-hand side, where I can say for both of these, as we go towards negative infinity, the limit doesn't exist, the graph is going towards negative infinity. And I look at the function as x goes towards positive infinity. Again, limit will not exist. There is no number it is approaching. Another way to look at it is there is no horizontal asymptote, and I can still see my graph is going in the negative direction. So maybe some comparisons to make. If we go back up to the top four functions we said all had odd exponents, and it looks as though if we have odd exponents, and I guess when I'm saying that, it should always be the largest exponent that you're dealing with in your polynomial. If the largest exponent is odd, we can see the graph will point in opposite directions. Okay. And I also notice it kind of looks like it's functioning, at least our top two graphs. This looks very similar to our basic parent function of x cubed. It has that same kind of behavior. And the only difference with the ones on the bottom is we have a negative. So if we think back to our transformation functions, if I have a negative x cubed, well, that would be a reflection. And if I'm looking at that reflection, since I've negated the whole function, negated the y, I'd be flipping over the x. That should make sense why this is flipping. Okay, same kind of an idea when we look at the bottom four. So we said these were all even exponents, and I see that our even exponents will point in the same direction. So even, and again, largest exponent, that's the one that we're always considering. Our even for our largest exponent, I notice that it will point in the same direction. If it is positive, so like these two on the left-hand side are positive, this is going to work like supposed to say positive, but my board just died. Positive, my function x squared, it's going to look like an x squared graph. They're both pointing up, they're happy, up like a cup. If they're both negative, or I should say if the leading coefficient is negative, well then I know it's going to point down, and it's going to work kind of like a negative x squared, again, doing that reflection. So these are just kind of some things that we can gather just by looking at these four graphs. So to summarize it on the next page, it's telling us that the polynomial function and the limits that we're dealing with are going to be determined by the degree of the polynomial and its leading coefficient. So I want to look at the degree of the polynomial. Again, that's that largest exponent, and its leading coefficient, meaning the very first function, if it's positive or negative. So if we were to look at these next two, we want to describe the end behavior. So I want to figure out the degree. Looking at this, I could tell you the degree on this is going to be a degree 3. That's my largest exponent. I can see the leading coefficient is positive. So in my mind, I'm thinking it's going to look like our parent function of x cubed. Okay, so if I had to describe the end behavior, and now this is especially true if we don't have a calculator. So as I go towards negative infinity, the limit's not going to exist, but it's going to go towards negative infinity. And if I'm going towards positive infinity, again, the limit won't exist. However, it's going to go towards positive infinity. And we can tell that by just the leading coefficient and the degree. Okay, same thing on B. If I'm looking for the degree, I'm finding my largest exponent, maybe not necessarily the first, but the largest, so it's a degree 4. And again, I'm noticing it's positive. So because it's an even exponent, it works like a x squared graph or a parabola. Because it's positive, I know it's going to open up. So my end behavior will be the same for both. So as x goes towards negative infinity, it's going to be the same exact thing as when x goes towards positive infinity. And they're both going towards positive infinity. The limit won't exist, but it will go towards positive infinity. Okay, some other patterns that we can see, and I know there's only 2 examples, but hopefully we can kind of generalize this and look at this more in class. We want to think about the zeros where it crosses the x-axis, and we also want to look at the max-min points. So if we look at this first graph, again, taking notice of what we just said the last time. So I have degree 3, and it's positive. So keep that in mind. We got a positive graph, degree 3. If I wanted to see the number of zeros, how many times this crosses the x-axis? Well, I can see only 1 time. So I only have 1 0 here. Now, the number of extremes, the number of max-min points. So I have 1 and I have 2. Okay. Over here, I have a degree 4, and it's positive. And if, again, I'm looking at the zeros, how many times it crosses the x-axis? Well, now this time I see 1, 2, 3, 4 zeros. And how many extremes? Well, this time I can see there's 1, there's 2, there's 3. Okay, so hard to maybe make a full comparison with only 2 examples, but we're going to talk about this, like I said, in class. A polynomial function of degree n. So maybe let's take a look at our example on the right-hand side. That's going to give us a better idea. So a polynomial function of degree 4 has at most the maximum number of zeros that this polynomial function can have. So a polynomial function of degree n has at most, we can see, n minus 1 local extremas. So we can see here degree 4, subtract 1, and I'm getting the maximum number of maximum points, and at most n zeros. So I had a degree 4 function, and I had 4 zeros. Now, notice we keep saying at most. That's huge. We got to get to that. Okay. So what if I wanted to find this algebraically? And we can. So maybe a little bit of review from last year. First thing we would do is factor out an x. We have x squared minus x minus 6. And from here, I want to find 2 separate factors, something that's going to multiply to be negative 6 and add to be negative 1. And our 2 factors are going to be, how about x minus 3 and x plus 2. So if we wanted to find the zeros, we would set each of these equal to 0. That means I'd have a 0 at 0, I'd have a 0 at 3, and I'd have a 0 at negative 2. Okay, notice the degree. The degree here is 3. So we said before we could have at most 3 zeros. In fact, we found all 3 zeros. This would also tell me we could have at most n minus 1, so 3 minus 1 or 2 extremas. Okay, so if we summarize this, it says if x minus k is a factor of the polynomial function, then the 0 of the function would be x equals k. That's what we found up above. So we had x minus 3 was a factor, the 0 is x equals 3. And if k is a real number, then k comma 0, whatever that k value is, would be your x-intercept of the graph. Okay. So this function below is actually already factored out for us, which is kind of nice, but this gives us a chance to take a look at something else. So if I wanted to just find the zeros, okay, so we set each of the factors equal to 0. So I have 1 0 here at negative 6. Set that equal to 0. I have 1 0 here at negative 3. Set this equal to 0, and I can see I have 1 0 at x equals 1.5. So these are our zeros. If I wanted to write these as x-intercepts, now that becomes a coordinate, negative 6 comma 0, negative 3 comma 0. And 1.5 comma 0. So these are all x-intercepts. These are all the zeros where they cross. Okay. Something to take note of is the exponents that we have. So now if I said to you, we had to find the degree of this, well, if I'm looking x cubed, I have an x squared, and I have an x to the first. So if I'm thinking multiply variables, I want to add exponents, so 3 plus 2 plus 1, that would give me a degree 6. So that could tell me I would have at most 6 zeros. Well, we only found 3. And I could have at most 5 max midpoints. Okay, and the graph below shows us what this function actually looks like. So we can tell more from our graph, from the zeros, by that exponent that goes with the factor. So a polynomial function has a real zero c. It says of odd multiplicity, odd exponent, then it will cross the x-axis, and there will be a sign change, meaning go from positive to negative or vice versa. If it has an even multiplicity, an even exponent, then it will not cross the axis, and it will not change sign. So if I take a look over here at the function x cubed, that's an odd exponent, and I have my 0 at -6, notice what it says. It will change. So it will be a 0, it will touch, but it will change from positive to negative. Notice this one. I have a 0 at -3, but it has an even multiplicity or an even exponent. It will touch but not change sides. And then here's my exponent at 1.5. I'm sorry, odd exponent of 1, 0 at 1.5. So since it's odd, it will change sides. So maybe a lot to process right now, a lot of little things, all interconnected. We will work on this more in class. I hope you liked this. Like and subscribe.